We're given position vector r of t, you can see it here, and we were asked to calculate various quantities, various vectors, unit tangent vector, component of the acceleration vector normal to the motion, etc. The usual stuff, similar stuff to what we've done in previous classes, but we want to be able to interpret this. We're going to want to be able to make a sketch of this vector function, a sketch of the graph that's traced out by this vector function for some interval of time, t. Okay, so interpreting t as a time parameter, our velocity is derivative of the position function r of t. Our acceleration is the second derivative. Derivative of our velocity, second derivative of our position. Again, something that's very familiar. And we take those derivatives, if we can keep from falling off the platform here. Okay, we take those derivatives and we get what we get, and it's obvious how to take these derivatives. I'm not going to read it to you. We calculate first the unit tangent vector. Now, the unit tangent vector is a vector of magnitude 1 in our direction of motion. Our direction of motion, of course, is the direction of the velocity vector, and we get a unit vector in that direction if we divide the velocity vector by its magnitude. And that's the same, of course, as dividing the r prime vector by the magnitude of the r prime vector. And, this expression doesn't assume that our parameter represents time. Okay, if our parameter represents something else, we're really not talking about velocity, are we? So it's equivalent just to say that the unit tangent vector is the r prime vector divided by its magnitude. Okay, well, the r prime vector, we have it right here, and the magnitude of the r prime vector we have here. And there's no mystery to where those quantities came from. I don't think anybody's having any difficulty with that. When we get into taking the derivative of this thing, everybody has difficulty. Okay, so and I mean everybody, even me. I could say especially me. Now, when you write this down, though, you do want to be aware that the sine squared t plus cosine squared t is 1. You always want to be looking out for that. So we're going to express this denominator as 1 plus 4 over pi squared times t squared. Okay, so here we have our unit tangent vector, and things are a lot easier if you have this, if you want to take a derivative, and I think we do. Much easier to take the derivative of this than this. You keep getting these sine and cosine terms, and they all kind of add up to 1, but you might not notice. If you didn't notice this, you might not notice it. So if you notice it in the first place, it saves you a lot of pain. Okay, so our t prime vector is our unit is normal. So if we divide the t prime vector by its magnitude, we get obviously the unit normal. Okay, that's one way to calculate the unit normal. We take the derivative of this thing, which is much less messy than this, but still, derivative's a bit of a pain. But we can do that. But another way to get the unit normal is to calculate the perpendicular component of the acceleration vector. Remember, this means that we're projecting our acceleration vector on the direction of our velocity. That gives us the parallel component of our acceleration. If we subtract that from our acceleration, we get a vector here which is perpendicular to the acceleration vector. So the a perpendicular vector is perpendicular to the motion, okay, and losing the train of my sentence structure here, but so the a perpendicular is normal. The n vector is our unit normal. If we do the a perpendicular divided by the magnitude of a perpendicular, we get the unit normal. Now that's the same thing we get if we did the derivative of the unit tangent vector divided by the magnitude of that derivative. And you really ought to calculate at least one of them both ways. And then, of course, to get a perpendicular, you recall what I just did with my fingers. To that A parallel is the projection onto the unit tangent vector of the acceleration vector, and that A perpendicular is then the A vector minus the parallel component. This being because if you add the parallel component of the acceleration to the perpendicular component, you get the acceleration. So here's your perpendicular component of the acceleration. Make sure you completely understand that. Also make sure you understand why I'm talking about a projection here, and remember how we do projections. Very important operation, and not that difficult to understand. Okay, so that's another way to get our unit normal vector. Okay, we'll continue in another clip.